I want to say a little more about inverse trig functions. We're mainly going to learn them by using them, but I want to have a video just about this and nothing else. So the notation can be a little confusing. Um, and so we have like the sign, and we would call this the inverse sine of 0.42. This would be the inverse cosine of 0.87, the inverse tan of 5.23. So we're taking a number it can come from various sources eventually, but for us, it's always going to be a ratio of sides in a right triangle. And it is going to calculate the mystery angle whose sine is that ratio. So it's the mystery angle in that triangle that corresponds to that trig ratio. So we'll see that in a second in the triangle case. That -1 power, I've said this in another video, that overlaps, unfortunately, with the notation for like a number to a -1 power. And you don't want to confuse it with that, which is a reciprocal. Very easy confusion to make. Partly to avoid that confusion, often we call it by a rather different name, the arc sine, or the arc cosine, or the arc tangent. You'll hear that and see that a lot, but we're not going to use that quite yet, just so that we don't have multiple notations for the same thing. But it's actually a very, very popular notation. And the arc there has to do with when we put trigonometry on circles. We usually wait for the next course for that, though. So again, something I mentioned briefly, but you want to think of this as the simplest example of this idea of an inverse function in general is when we study roots, and that is an operation that undoes powers. So we know, for example, that 6 squared is equal to 36. That's not super hard to understand the forward direction of putting 6 into the squaring function. Let me say that explicitly. We are putting 6 as an input into the squaring function, the machine that takes any number and just outputs its squares. And now we want to know how to undo that. And that's the very general idea of an inverse function. And so here, how do you know, what's the definition of the square root of 36? It's the mystery number x such that x squared is 36. And very, very often, and this is true eventually for trig functions as well, we actually have to say there might be multiple answers. Right here, there's two numbers, 6 and -6, that solve that equation. But to make an inverse function, we always have some sort of rule that says, here's the one we really want. Almost always we say we want the simplest answer. For the roots, the convention is we use the non-negative root. Okay, so that's the thing that people often get confused by. The square root of 36 is just 6. It's not plus or minus 6. If you need both, you actually put the plus or minus in front of it artificially. But so this will connect with some important things about inverse trig later, when you can get confused about what possible answer you want. That shouldn't be an issue here, but I wanted to highlight it right now. So it's what's the mystery input to the squaring function, here 6, that would produce the output we're seeing, which is 36. Okay. Now, more complicated is going to be like the square root of 29. And the calculator knows that. Let me actually get those little invisibles out of the way. Is about 5.3852. And how would you check that? Of course, you would calculate 5.3852 squared. Okay. And it knows that that's equal to 29. Okay. So that's, again, an analogy. We know this operation of squaring and we undo it. That's something that's a very nice analogy for the trig stuff. So back to the trig. We have an angle in a right triangle. Here, the angle A is what we're going to be. So here, look, at angle A, okay, in this diagram. And we'd like to get the measure of that angle. If you know all three of these sides, there's actually 3 ways to do that. Now, very, very often, we're only going to know 2 of those sides. Let me make that a little bigger. The numbers are not quite clear there, I think. Okay. But suppose we only knew the opposite to A and the hypotenuse. That is plenty to get the mystery angle. We just say, okay, 5/13, that's a certain number. And that's the ratio. That's what sine of the mystery angle A would give us if we knew the angle. Since we know the 5/13, we're undoing that. And we say, what's the mystery angle whose sine is? That's how you would think about that symbolism right there. The mystery angle whose sine is 5/13. And then once again, we're going to have to get that out of a calculator or a computer. It turns out to be 22.6 degrees. Now, if we, in this situation, if it was actually the 12 and the 13 that were known, oops, it's doing weird things. That's fine. We should get the same angle. I just want to see the same picture. We should be able to get that same angle from cosine. The inverse cosine of 12/13 is another way to get that if we knew that information. Or we're going to see situations where yeah, it's wanting to give me extra space here. Okay. I know. Let me take that out. It's got a lot of extra spaces that I don't want. And voila. And voila. Okay. So I just want to be able to see the picture. Okay. Inverse tan of 5/12 is going to be that same angle. Okay. Now there's nothing saying that it has to be any nice numbers. I picked one that's familiar. We know 5, 12, 13 is actually an honest to God right triangle. But if we go over to GeoGebra, we can see here's a more random side lengths in a triangle. And for example, I've got it calculating inverse tan of 3.22 over 6.98. So opposite over adjacent. So that would be if you knew these two numbers and maybe you didn't know the hypotenuse directly or you didn't want to use it. And it's calculating that as 24.76 degrees. In fact, with dynamic geometry, it's kind of fun. I can just put that in as inverse tangent of whatever this length is, BC, over whatever the length AB is. And that turns out to be, well, it's still 24.8, of course. But now, if I make that taller, we can see this angle down here increasing into the 30s or decreasing. And it's just going to be tracking exactly what that angle is at A. One more thing, real quick. If you try to put in inverse sine of 1.27, your calculator will give an error, and that's absolutely correct that it should give an error, because you're saying, what's the mystery angle in a triangle where the opposite over hypotenuse ratio is bigger than 1? Wait a minute. That would mean the opposite, one of the legs of a right triangle, is bigger than the hypotenuse. That's absolutely impossible. The hypotenuse is always bigger than either leg. So if you're tempted to put in, if you're doing a calculation and you're saying, oh, I'm pretty sure I take inverse sine of 1.27, you put it into the calculator, it gives you an error. That's not the calculator screwing up. It's a sign that you've put in the wrong input to that inverse sine function. Sometimes it's as simple as you took hypotenuse over opposite instead of opposite over hypotenuse. Similarly, this number, putting in the input of an inverse cosine, shouldn't be bigger than 1, because that would be something where the adjacent side, one of the legs, is almost 3 times as big as the hypotenuse. So watch out for that. That error, if you go to the calculator, it gives an error, don't just be like, I don't know what to do. It means that you've looked at those ratios wrong. Now, rather different is the inverse tangent. That can accept a number that's arbitrarily big. So like here, it's calculating inverse tangent of 17.12 is 86.7 degrees. That's totally reasonable, and this number really can be very big. When is that going to be big, though? It's going to be big when opposite over adjacent is really a big ratio. That's going to be, let's go back to GeoGebra. That's going to be where, let me make AB really small and BC really big. When that ratio is big, that's a very big angle close to 90 degrees, and this is very steep, and we see that the inverse tangent of, well, actually that's not huge. Let's make it even smaller. this really, really tiny. And it's going to be a little slanty, but that's okay. Whoa, sorry. Okay. Now we're getting an angle that's very, very close to 90 degrees. Okay,